Okay, so first of all, I wanted to thank the organizers for the invitation. It's really a pleasure and an honor to be the first speaker at this event. And during this course, what I'd like to talk about is Bernstein-type theorems for some nonlinear geometric PDEs. Bernstein theorems. Okay, so Bernstein-type theorems are going to be theorems related to the rigidity of global solutions to the equations under study. So rigidity of global solutions. And that has its origins in a theorem of Bernstein from around 1915, who proved that entire minimal graphs in R3 have to be flat. That's sort of the precursor to the result of Ducarmo and Peng that was mentioned a few minutes ago. And the particular PDEs that I like to focus on during this course are the Monge-Ampère equation, it's a fully nonlinear PDE that arises in many geometric contexts, as well as the minimal surface equation. And the ideas that are going to be used to study the Bernstein-type problems for these equations are actually extremely versatile, and they're also used to study lots of more complicated problems. So, for example, the minimal surface system. We study minimal surfaces of higher codimension, or the special Lagrangian equation. Which is the minimal surface system, but restricted to the case that the maps you're studying have a potential, or other fully nonlinear equations like the sigma k. I may touch on those as we go along, but I probably won't have much time. Okay, so overall, the plan of the course is going to be, today, I'd like to study these equations in two variables. So in 2D, these are going to be a little bit simpler. We can have a unified treatment of the Monge-Ampère minimal surface equation. Turns out by doing clever changes of variables. And then when we go to higher dimensions, we're going to have to study them separately. So tomorrow I'd like to talk about the Monge-Ampère equation in higher dimensions. Which is more in the direction of fully nonlinear PDE theory. On the third day, I'll talk about the minimal surface equation in higher dimensions, and that might have a little bit of connection with what Professor Urbano will talk about. Finally, on the last day, I'd like to talk about how you construct some sort of counterexamples to Bernstein theorems in high dimensions. So we'll talk about the construction of nonlinear global or entire minimal graphs. Nonlinear entire graphs. In particular, I like to do an exposition of this Lombieri and Joji-Giusti example from about 1970. Okay, so that's the plan. And before we jump into doing the Monge-Ampère minimal surface equation, something nonlinear, I like to start linear, because almost all the theorems we're going to prove have their origins in some linear problem. So let me just recall what the basic Liouville theorem is. So today is going to be very concrete, very straightforward, very easy. It's going to ramp up as the time goes on. So be patient. Basic Liouville theorem. This is a theorem about harmonic functions. So this says that if you have a harmonic function on n, and it happens to be non-negative on one-sided bound, then we can say that the function is a constant. Okay, so just to warm ourselves up, I want to spend just a couple of minutes on this. So what is the idea of this theorem here? The idea is the following. The idea is that if the harmonic function that you're considering had an interior minimum at some point, then we get a contradiction of the strong maximum principle. The strong maximum principle would imply that it has to be a constant. So, strong maximum principle rules out this picture right here. And because we have a lower bound, we can sort of intuitively think that you should have a minimum. Of course, the proof needs to quantify this idea in some way. Because I'll return to what the idea of the proof is tomorrow, I'd like to just do it in 2 lines. So the actual proof uses the mean value property. So if you add a constant to the function, you can assume that its infiniment is 0. And then by translating, you can guarantee that the value at 0 is extremely close to 0. So also with Hellas generality, u at 0 is smaller than some very small number epsilon of your choice. Okay, so we know that solution is very close to 0 at the origin. And the first thing we're going to do is to use the mean value property. So the mean value property says that the average of u in any ball centered at 0 is very small. So u kind of has to look, on average, very, very small. But it might have a few spikes. So the mean value property says that the average in any ball of radius r around 0 is small. And what we like to do is to rule out upward spikes from occurring in the solution. And for that, we use the mean value property one more time. So we want to say, well, why can't this happen right here? The idea is if u was large somewhere else, then the average would also have to be large, and that obviously contradicts this picture. So if x is in the ball of radius r over 2, for example, what we have is that u of x is the average in the ball of radius r over 2 of u. So maybe this is ball radius r, and x is right here. We're taking its average in ball of radius r over 2. And this we can bound above by that up to a constant. This is smaller than the average in the ball of radius r. So up to a factor of 2 to the n, just coming from the change in volume. And this we know is smaller than epsilon. So we concluded that in a ball of radius r over 2, u is less than epsilon up to a constant. So that since epsilon was arbitrary, we're done. We can set r to infinity, epsilon to 0. We get okay. So I wanted to spend a little bit of time on this because when we talk about fully nonlinear equations, the idea for proving some sort of Liouville theorem is very much along these lines. You want to prove some sort of mean value property for more general linear equations. And that was provided by breakthrough theorems of DeGiorgi and Nash, Pirov, and Stefanov. This is the basic. Okay. And just as a remark, because today we're going to focus on 2 dimensions, now I'm going to start focusing on 2D. In 2D, you can say something, say something a little better than what we said. So if n is equal to 2, you just need a superharmonic function. So a superharmonic function which is bounded above, below the 2D is constant. I just want to mention the proof because it will come up. The idea will again come up later. In 2D, the point is that the fundamental solution of the Laplace equation, the log, is unbounded from both sides. It was this log trick. So we'll do a maximum principle version of this log trick. What you can do is the following. By sliding the graph of u up or down, you can guarantee that the minimum in the ball of radius 1 is going to be achieved in 0 on the boundary of the ball of radius 1. Infimum the ball of radius 1 of u, which is the same thing on the boundary, is 0. Just by adding a constant to u, we can guarantee this in the case. And the infimum is taken on the boundary just by the maximum principle. Superharmonic functions take their minimum on the boundary. And the idea is to construct a barrier for u outside of this ball, which is a small multiple of the function log. So here is the function minus epsilon log x, which is a harmonic function away from 0. And the point is that this function log is unbounded. So if I look at this function here, for sure it's going to lie beneath u on the boundary of the ball of radius 1, because it's 0 there. And furthermore, if you go very, very far out, this tends to minus infinity. Because of the lower bound that we have on the function u, it'll eventually lie beneath u. It's also less equal to u, boundary of all of radius r, and r is sufficiently infinity. So from the maximum principle, we can conclude that u is larger than x outside the ball of radius 1 for any epsilon. If you take epsilon to 0, we see that u is non-negative. But what do you know about non-negative superharmonic functions which vanish at a point? They have to be constants by the strong maximum principle. So because u vanished somewhere on the boundary of the unit ball, strong maximum principle apply to u is 0. Strong maximum principle. Okay, so that's the idea of how you can get a stronger result in 2D. There are other proofs that are based on integration by parts that are very much related to how you prove the Bernstein theorem for minimal graphs as well. I'll leave those. Okay, so that's just a lightning review of the Liouville theorem. Any questions before we go on? Yeah. Good question. So the point is that in higher dimensions, if you look at the fundamental solution, it's 1 over absolute value of, for example, in 3D, it's 1 over absolute value x. And so it's not unbounded from both sides. That's the issue. And in fact, if you take 1 over x and you just cap it off with a parabola, for example, then you get a superharmonic function, which is non-dual constant. Good question. Any other questions before? Okay, great. So now I'd like to move on to the Monge-Ampère equation in 2D. And the theorem I'd like to prove is the Bernstein, or the global solutions theorem. So this in 2D is due to Jurgens in the 50s. The theorem is that if you have a solution to the Monge-Ampère equation, which is the determinant of the Hessian of U is 1, and R2, and you don't even need to assume anything else other than this, no growth hypotheses, nothing else, just this equation, you can conclude that U is a quadratic polynomial. Okay, so at first when I see a theorem like this, I find it a little bit surprising. You don't need to assume anything but the equation and you automatically get a rigidity result. But I think one way that rigidity comes in is that if determinant d squared u is positive or negative, say it's positive, then u has to be convex or concave. That's a very rigid situation. So already that means it's kind of as bound, one-sided bound on the hash. So one of the key things here is that Q is convex. All right, so there are a lot of proofs of this theorem in 2D, but I'm going to give my favorite proof because the method that we'll describe generalizes to the special Lagrange equation. So the proof is based on studying the graph of the gradient of U, which is a two-dimensional object in R4. And we're going to perform a rotation of it. So the proof is going to be what we call the Legendre Levy transformation. So in this picture, the horizontal line represents a copy of R2, as does the vertical line. And the graph of the gradient of U I'm going to draw as follows. It looks something like this. Sigma instead of all x, gradient of x. And I've drawn it as a 1D increasing function, and there's a good reason for that. The reason is that if we're dealing with a one-dimensional convex function, that means that the derivative is increasing. And so this is like the graph of the derivative. I want it to be an increasing function. And there's a clever change of variable that you can do when you look at the gradient graph, which is going to make life a lot simpler. The idea is to rewrite this graph, or take this gradient graph and perform a rotation of it by pi over 4. So another way of saying this is I'll take new coordinates given by an SU2 rotation. So these are x tilde, y tilde, given by x tilde, y. Which was just a rotation of the coordinates in R4. And what I want to do is to rewrite sigma as a graph over the x tilde coordinate. So we're trying to rewrite it as a graph of some map G of x tilde. Sigma set of all x tilde. Or you can just use these relations to write down what G is implicitly. G of square root 2 times x is equal to 2 of x. Square root 2 times x. So here I'm just replacing y with x. I think a natural question at this point is, how do you know that sigma is still a nice global graph over this x tilde plane? Well, the point is that this here is the diffeomorphism of R2. I'll leave that as an exercise for you guys, but the point is that it's the gradient of a nice uniformly convex function. If you write it written as x, gradient of using the fact this is a uniformly convex function, you can show it's like so what is this actually accomplished? Well, we need to rewrite the equation in terms of G. And if we differentiate this once, let's see what we get. We get that the derivative of G is going to be minus the identity plus U times, and I'm going to use the chain rule and move a matrix over. Inverse. So here I'm just taking the derivative. On this side, I'll get a copy of identity plus d squared u. I'm just multiplying inverse. What can you see from here? We'll be able to read off everything from this expression. So first of all, notice that these two matrices are simultaneously diagonalizable. This is just d squared identity, of course, is not going to change anything. D squared u is appearing in both. And by the symmetry of this matrix, you can show that this thing is symmetric. So we'll get that also as a small exercise. This thing is symmetric. And something we know about maps whose differentials are symmetric, that means that they're curl-free. And that's the same thing as having a potential. So G is a gradient of something. Some function. Also, if we look at the eigenvalues of Hessian u tilde, so this here then is going to be d squared u tilde. The eigenvalues tilde. We can write them in terms of the eigenvalues of d squared u as follows. If I just write these, choose coordinates in which these are diagonal matrices, it becomes very easy to write down. Eigenvalues are going to be -1, 2, lambda I are the eigenvalues. D squared U. All right, so now we're going to use the modular pair equation. We know that the product of these two is 1. So if we use that over here, allow me to rewrite the first guy by multiplying the numerator and denominator by lambda 2. Multiply by lambda 2. 2. We'll get a minus lambda 2 plus 1 over 2 plus 1. Just using this relation. And now here's where the magic happens. Now you notice that the sum of these two things is 0. In other words, U tilde is harmonic because the sum of its Hessian eigenvalues is 0. And moreover, these two things are bounded by -1 and 1. Because lambda 1 and lambda 2 are positive numbers. If you just look at this guy, it's for sure going to be. And now we'll just use the Liouville theorem for harmonic functions that we've just proved. So Liouville theorem will imply that U tilde is a quadratic polynomial. So really what I'm doing is applying the Liouville theorem to two derivatives of U tilde, which is a bounded harmonic function. And therefore the second derivatives are constants. I think we can finish on time. And at this point, we're done because if d squared U tilde is constant, or if U tilde is a quadratic polynomial, that means that the gradient graph of U tilde is just a two-plane. And if you represent it in the original coordinates, it's still just the graph of a linear function. Therefore, the gradient of U has to be. Okay. So minus the details, the trick was that if you start off with some convex function, solves the modular pair equation, and you rotate the gradient graph, then it has a new potential which happens to be harmonic. It's a little bit magical. But let me just make a small remark, which is that this is an instance of what happens for what's called the special Lagrangian equation. This method generalizes which is an equation which can be written as the sum of arctans of Hessian eigenvalues is a constant. So the case that we've just done corresponds to the case that mu is pi over 2. The reason is that the arctan of a number plus the arctan of its inverse is always pi over 2. Okay, so this equation, where it comes up is in the calibrated geometry. So it turns out that if you have a solution, well, these are of course the eigenvalues of the Hessian function. So the gradient graph of a function which solves this equation happens to be volume minimized. And that's where it arises in geometry. But the point is this, is that if mu is 0, then it's just harmonic, the Laplace equation. If mu is non-zero, what you can do is you can do a same rotation trick. If you rotate instead by an angle of mu over 2, then you'll end up getting a harmonic function of boundage. So that's just a small sign. Okay, maybe I'll say one more thing. I think that if you were to study the special Lagrange equation first, instead of looking at the motion pair equation, you'd be much more quickly guided to this trick. And the reason is that this rotation makes the arctan of these change in a very simple way. So if you have, so arctan of lambda I is just going to be this angle in this picture here. If you perform a rotation by a certain angle, then you're just changing the arctan by a constant. That's why it's such a, such a natural tool if you view the motion pair equation in 2D special equation. Okay, and then the last part of the talk, this first lecture, I wanted to do something on the minimal surface equation as well. So I think we can do this reasonably quickly. So this is a theorem of Bernstein. Just that if U on the plane solves the minimal surface equation, divergence of gradient U over square root 1 plus root 2 squared. Then U is linear. So it's another remarkable statement, which is that a function on all of the plane, simply by virtue of the fact that it solves this nonlinear geometric PDE globally, gives you a very strong rigidity. It has to be a linear function. And I think in the last 10 minutes, I can sketch out a proof of this, which will rely on what we did for the motion pair equation. The proof is going to be the following. So what this equation here reflects is it reflects that U is the critical point of the area function. The graph is a critical point of area. So equation tells us that for A of U, given by an integral of square root 1 plus beta squared, U is the critical points. A of U plus epsilon times any compactly supported smooth function is going to be the same thing as the area of U on some domain plus middle O of epsilon. So in other words, if you take the graph of U and you make a small vertical variation by phi, then you're not going to change the area of the graph to leading over epsilon. All right. So this is what's called like the outer variation. If you take this outer variation, this whole thing is equivalent to this equation being solved. But it turns out that in some scenarios, looking at what's called the inner variation is helpful. And that's what happens when you take this graph, but instead of doing upwards deformations, you do side-to-side deformations. So for inner variation, what you have is that the area of the function u composed with a small deformation of the independent variable. Here V is a compactly supported smooth vector field. This should be a area of U. Epsilon. And what I want to do is to write down what system of equations this corresponds to. And there should be two equations because we can vary horizontally in two different directions. Okay, so how you can calculate the inner variation equations is the following. Just draw a picture here. If you make a little deformation side by side to the side of the graph of u, so you shifted it by epsilon times the vector field v side, that will correspond to a vertical variation. That's like epsilon gradient u dotted with the vector field. So one quick way of deriving what the inner variation equations are is to look at an outer variation that has this special form. You know, for say f of grad u is the square root of plus at the integral of gradient of f at gradient u dot any compactly supported smooth thing is going to be 0. That's the outer variation equation, so we'll plug this in. Okay. And then if you write this down, what this is, you integrate it by parts. In the interest of time, we're just going to write down what it is. It's going to be pk times di of f gradient delta ik minus 5 gradient u. Here what I've done is I've just passed the derivative here. I recognize that as the gradient of just gradient u. When the derivative hits v, I integrate by parts and I get something like this. So I'll just say integrate by parts. All right.
So there v is also depending on I.
These.
Where does I come from?
So if I write this as, where does I come from? It's like PI. Great. Okay, so then what we know is that this expression vanishes for each k. Yeah. Okay. Okay. 0 is 1, 2. And now I'll leave it as an exercise to check that this matrix, this is like saying that the divergence row-wise of a certain 2 by 2 matrix is 0. In this matrix, you can check for this choice of F is symmetric. And it has determinant 1. And this is very special to the 2 by 2 matrices. Oftentimes in the geometry literature, what you'll see this written as is the divergence of the square root of determinant G inverse 0, where G is the matrix identity A into U. It's a gradient U. Here's a way of writing things in more geometric notation, where G is like the metric induced on the graph by the parameterization x, x. This is very clearly a symmetric matrix. M of x symmetric. And the determinant equaling 1 is very special to 2D. If you take the determinant, you'll have 1 over determinant G from this, and another copy of that. Determinant G coming out. Take the data of that. Okay, so now in the last couple minutes, I think I can just do a little bit of magic really quick. So if we have the divergence of something being 0 in 2D, the divergence of a vector field being 0 means that it's the perpendicular of a gradient. So 0 is the same thing that is gradient perp.
You can take some minutes.
Okay, I'll take
All right. Okay.
maybe a couple extra minutes. Thanks. So the divergence of this matrix being 0 can be rewritten as follows. This matrix, M of x, is going to be the rotation of a gradient. So d of some function w times j. Where w is some map from R2 to R2, and j is a rotation matrix. This is just 2D calculus. And from here, we're going to find our way to the Legendre equation. So we have this. One way of rewriting that, if we left and right multiplied by the matrix J, is that J times W. So you've just taken this, multiplied on the left and right by the matrix J. And the reason I wanted to do that is because this is the derivative of some map from R2 to R2. And this is symmetric. And that follows from the symmetry of M and the fact that J transposes minus J, but there are two of them here. Okay, so again, we have the derivative of something being symmetric. That means that this here has to have a potential. So JW is a gradient of some function phi. This thing here is therefore the Hessian of a function. And the determinant of this, as we mentioned, is going to be 1. Okay, so the point was this, is that when you look at the inner variation system, it's somehow amenable, it's a nice symmetry. It's amenable to doing some 2D calculus and finding a potential. And it's a little bit magical that this potential has to solve the motion equation. But it does, so we can apply what we've done. We know that t squared of phi has to be a constant. By the previous theorem, by the European's theorem. And if we trace back, that means that this matrix M is constant. Our square root determinant G inverse is constant. G is magnitude. And from here, it's a small exercise to show that this being constant implies that the gradient of U has to be constant. So I think that this approach to the Bernstein theorem is due to Nietzsche. But the original proof of Bernstein's theorem looked a lot different from this. This is a very much cleaned up version of what Bernstein did originally. But since I'm out of time, I'll stop there.
Thank you, Roger. Time for questions. We have 5 minutes for that. Any questions?
In order to see inner variation after variation, because you need a minimal regularity of the map.
That's right. That's right. You need it to be W21, for example, will be good enough. So you need to have 2 derivatives.
Yeah.
And the reason is that you have an outer variation involving the derivative of U.
Yeah.
And you need to differentiate that. So.
But is it even suitable because like or
This is a good question. So if you just have, let's say, a Lipschitz minimal graph is automatically going to be smooth by some orthoregularity theory. Although in 2D you can get around it, but in hierarchy it's the Georgi-Nash-Bose theorem.
Any questions or comments? No? So thank you, Connor, for nice talk.